Are the polls released?
This one is released.
All right. I have some damage to show for it. Oh, that's actually a 2-inch by 1-inch laceration on both hands. I'm very proud of it. And I got bitten by a giraffe. I got bitten by a giraffe. It just happened. We saw you on the new Discord. Are you coming next Saturday? I miss you. I don't know. It just happens. You have no choice. Okay. Just can you pull up the fake names? Yeah. Okay. All right, folks, everybody sign up for attendance, please. And good morning, Shivan. Okay, let's start. The usual stuff for all 7, 8, 9, 10 of you. Okay, the numbers are improving. That's 4% of my class is in the class. Again, I apologize for missing the class on Monday. My flight got rerouted. I was just telling the guys, I was supposed to fly from Nairobi to Addis Ababa and from there to DC. And about 2 hours into the flight from Nairobi, I woke up and looked at the tracker and it said Djibouti. So I went up and asked the stewardess, why is it showing Djibouti instead of Addis? Am I on the right plane? And she says, really? And then she rushed off to talk to the captain, and apparently we were out of fuel. So we got rerouted to Djibouti, where we spent a few hours, and I missed my flight. And so here I am 1 day later, right? And that's why we have a class on Wednesday and Friday. Somehow this semester has been very exciting. All right, let's begin. We went through a whole lot so far. We've seen, to start off the course, that neural networks are universal approximators. They can model any Boolean categorical or real valued function. They can look at static inputs for patterns, MLPs. They can scan for patterns. These were your CNNs. They can analyze time series for patterns. These were your recurrent networks and your transformers. And they must be trained to make their predictions. But this is at the surface. What happens inside? What does the network actually learn? So, and what does it learn to represent? This is what we're going to be looking at today, right? Here's the problem of learning in the network. This is how we defined it. You're given a collection of input-output pairs, a collection of training instances where you're given the input value and the desired output value. And from these, you must learn the entire function. That's the target. So, for example, if you wanted to train a network to perform classification, you might get training data of this kind, where all the red data represent class 1 and blue data represent class 0. You wouldn't see the boundaries, you'd only see the training points. And from these training points, you must learn a function like this one, which is an output of 1 inside the double pentagon and a 0 outside. But in reality, you're not going to get data like this. You're not going to get this cleanly separated data where you have only red data inside the a positive region and only blue dots, a very negative region, you're going to get stuff which is more mixed like this. You're going to get the odd blue instance inside the red region and the odd red instance inside the blue region. So the classes are not going to be cleanly separated. So what really do we learn? To understand what's going on, let's start off by looking at a very trivial linear, very trivial example of a single perceptron, a single linear classification problem, where we're given two-dimensional data. The blue dots represent data from one class, and the red dots represent data from the other class. Let's just, without loss of generality, assume that the red dots represent the class 1. So what we really want, if I'm just training a simple linear classifier, is to find a hyperplane that separates the red dots from the blue dots. So you want to learn a function like this, a Heaviside function, which takes a value of 0 on the blue side and a value of 1 on the red side. But then you have a problem. If you look at the data, there is no line, there is no hyperplane that cleanly separates the two. There are some red dots suspended in the air on the blue side and some blue dots lying on the ground on the red side. You're not going to be able to draw a hyperplane, a Heaviside, which puts the blue on one side and the red on the other side. So what exactly are we learning? Now let's simplify the problem further. Let's look at it let's look at a one-dimensional example where the inputs just have a unidimensional value x, and the class can either take the value 0 or the value 1. So your training data might look something like this. The blue data belong to one class, and the red data belong to the other class. Now in data like this, for one-dimensional data, what is a linear classifier? What's a linear separator? Anyone? Pardon me? A line? No, this is, the y-axis is the class, right? So what would a linear separator be? Pardon me? A separator, I want a classifier, right? It's going to be a threshold. You're going to say anything on one side is class 0, anything on the other side is going to be a class 1. And there is no linear separator out here. So you cannot find any threshold such that all data on one side are red and all data on the other side are blue. Now, our neural network is a universal approximator. If you just provided these things as training data, it can learn any function. There's nothing stopping it from learning this hideous function over here, right? But is this the function we really want in this example? No, right? And even if you say, I'm happy with learning a function of this kind, just for argument's sake, what if I gave you data of this kind where I have several training instances at exactly the same x, but some of them have the label 0 and the others have the label 1. So for example, let's say I have many training instances at the exact same value x, say 100 of them, and 90 of them have the label value 1, red, and 10 of them are labeled 0, blue. So what must the output of the network here be? Would you want it to be 1 or would you want it to be 0? 1? 0? What would you want the network output to be? 1. Are you sure? Is there something better than 1? Again. Would you want 1 or would you want 0.9? Which makes more sense? The 0.9. Why?
More representative of the entire system.
It's actually, the 0.9 is telling you the distribution of data at that x, right? It's telling you that 90% of data at this value of x belong to the class 1 and 10% belong to class 0. Now, how you use that information downstream is up to you. You can apply any odd threshold to this probability to take your decision, but this is far more informative than just saying if the value is this x, then the output must be 1, right? Do you agree or not? Can I hear a yes?
Yes.
Thank you, right? I know all of you are sleeping. So let's say we take this for granted, okay? But then I do something very simple. I perturb, all of the training instances. So I still have 100 training instances at that x, but not exactly at that x. They're all off by 10 raised to minus 17, which is the resolution of your floating point number, right? And so no two values have exactly the same x. They're slightly off. And 90 of those are class 1, and 10 of those are class 0. Now, do you want to learn this ugly function which goes up and down rapidly, or do you still want a value of 0.9 in this region, which makes more sense? Can you see? 0.9 makes more sense, right? An infinitesimal perturbation should not change your functions in such an arbitrary manner, right? So how much of a perturbation are we willing to tolerate before we say that it should no longer be 0.9? How do we know, right? We can't really know. But then let's change our perspective. Let's say at every x, instead of just looking at that x, I look at a small range of values around that x. And my target output is going to be the average of all the y values at that x. So in the earlier case, if I looked at a small window around this x, the average was 0.9. So it made sense for us to say the output must be 0.9 over here, right? I'm going to use the same logic everywhere. So at this location, it will be, what's the average going to be in my example? 0, right? As I keep sliding right, what will happen? Can you speak up, please? The average is going to keep going up, right? And eventually, you're going to be seeing only once. This is what the average is going to look like, right? And so this is the function that we really want to be modeling. This characterizes what is happening in the data much better. And what does this function actually represent at any x?
Probability that the output is 1.
Here, this function represents the probability that y equals 1 at any given x, right? So, or it's an approximation of the probability. There's a question that I left unasked, and what is that? When I draw a picture like this, what's the first question you should have asked me? Anybody?
What's the range of x that you're looking at?
What is the width of the window within which I'm averaging things, right? I just made an arbitrary statement saying I'm going to look at a small width of range of x, and I'm going to average the y's within that x. And as it turns out, we don't really have to consider it. We'll see why. But anyway, so this function is the logistic regression function, the smooth function which goes from 0 on one end and smoothly goes up to 1 on the other side. And what is the logistic regression function? You guys are familiar with it? What was this? This was the, what was this function? Does this ring a bell? This is a sigmoid activation, correct? And so that's why we use a sigmoid activation. A sigmoid activation actually has this characteristic that it goes smoothly from 0 to 1. And it has this formula, 1 over 1 plus e raised to minus w0 plus w1 x. If x, let's assume that w0 and w1 are both positive, right? If x is a large negative number, then what is e raised to minus w1x? If x is a large negative number, what is e raised to minus wx? Anybody? Guys, blessed, what is it?
That's e to the power of infinity.
It'll be?
E to the power of infinity.
A large positive x, negative x is going to become e raised to minus x, where x is a large negative number, is going to become e raised to x. X is a large, so, and so, wait. It's going to be e raised to a large positive number, right? And so that's going to become infinity, and 1 over infinity is going to become 0, right? What if x is a large positive number? What does this become? The exponent becomes 0, right? E raised to minus x becomes 0 for x being a very large positive number. And so 1 plus 0 is 0. And so the overall function becomes 1. So when x is a large negative number, you're going to get 1 over a very large number, which becomes 0. And so this is going to be 0, right? When x is a large positive number, this is going to be 1, and in between is going to curve smoothly. And so that's why you get this kind of behavior, right? So far so good. And in fact, this is your perceptron with your sigmoid activation. You have some x going in, you have some weight, you have some bias, and this function is going to go smoothly from 0 to 1. And the exact location at which it crosses over from being closer to 0 than it is to 1 is determined by the bias W0, and the rate at which it changes is determined by the weight W1, right? Okay, so questions? No, okay. And this thing, so the sigmoid perceptron with a single input models the a posteriori probability of the class 1 given the input x, as we just saw, okay? That was for a one-dimensional input, but the same thing happens for any number of dimensions. So if I have this two-dimensional example, I'm going to have the actual data. You're not going to get a clean linear separator. You're going to get some blue dots on the red side, some red dots on the blue side. And so you will not be able to draw a nice heavy side step function where all the ones are in all the red dots are in the 1 region and all the blue dots are in the 0 region. Instead, what we want to plot is a sheet of this kind, where at each point, the height of the sheet gives you the probability of the class 1 given the input x. And when you're learning the perceptron, what you're really doing is learning the rate at which the sheet goes up and the orientation of the sheet. So W determines both the rate and the orientation, W1, and W0 determines the position, right? Okay. So the sigmoid perceptron now is a linear classifier. Function is a curve. Why am I calling it a linear classifier? Anybody? Who wants to take a shot? Why is a curve a function which looks like this, a sheet of this kind, a linear classifier? Is the function linear? No. Okay, so why is it a linear classifier?
Because it's classifying only in one dimension. The outputs of the classification are only along the y-axis or the x.
No, but that doesn't mean it's linear, right? So why is it a linear classifier? Anybody? Boundary, yes. So your function looks like this, right? It's a sheet of this kind, as we saw. And so this height, maximum height is 1, the minimum height is 0. And I can say that and the function represents the a posteriori probability of the class 1. Now I can say if the a posteriori probability of the class 1 is greater than 0.5, then I will assign it to class 1. If it's less than 0.5, I will assign it to class 0. So where is the boundary at which the function goes from being above 0.5 to below 0.5? That boundary is going to be a line. Something of this kind. So if you look at the function from the top, and you look at the region where the function value is greater than 0.5 and the region where the function value is less than 0.5, the boundary between the two is going to be a line, even though the function itself is not a linear function, which is why this is a linear classifier. Make sense to everybody? Okay. Can I get an enthusiastic yes? Yes. Thank you. Okay. And so now, let's go back to our earlier problem. I wanted to learn this function, and I said I'm going to look at a small range of x's as I'm sliding left to right. What is the width of this range? We're never actually going to explicitly look at the width of the range. Instead, the way we deal with it, we are given many training instances, xy pairs, where you have the x and the corresponding label y. And from the xy pairs, we're going to learn the W0 and the W1 for the function directly. Now, for this, first, what does the sigmoid actually represent? The sigmoid represents P of y equals 1, given x, which is 1 over 1 plus e raised to minus W0 plus W1x, right? So what is P of y equals 0 given x? What is this?
1 minus this.
1 minus this term, right? Which is going to be 1 minus 1 over 1 plus e raised to minus w0 plus w1x, which simply becomes, if you work it out, I can take this to the numerator, subtract things, it becomes 1 over 1 plus e raised to plus w0 plus w1x. This making sense? Okay. Can I write both these formulae in a single form? Anybody? So instead of calling this y equals 0, I can say y equals minus 1. 0 and minus 1 is the same as 0 and 1 are binary, as are 1 and minus 1. So I can choose my labeling, right? If I call this y equals minus 1, then observe that this is simply minus of 1, and this is minus of minus 1, right? Everybody with me? And so what does that become? So this is just y, and this is also y. Make sense? And so I can just write this as p of y given x equals 1 over 1 plus e raised to minus of y times w0 plus w1x. Okay? So everybody with me? Okay, now, if I'm given a bunch of training data, I want to learn the function, and I can use a time-tested method, the method of maximum likelihood, which says that of all the possible models in the world, you want to choose the model, or rather the model parameters which maximize the probability of your training data. And so here your training data are this set of, let's assume IID pairs, training instances, where each training instance is an XY combination. So the total probability of your training data is the product over all training instances of P of X comma Y, which I can use Bayes' rule to separate out as P of X times P of Y given X. And now, using our sigmoid formula, our logistic regression formula, we know that P of Y given X is this guy here. Just the sigmoid with the Y baked in, right? And so now, if I want to train the model using maximum likelihood, I'll consider the probability of the training data, or more conveniently, the log of the probability of the training data, because we know that maximizing the probability of the data is the same as maximizing the log probability, right? And so I can write this as the summation over all training instances of P of X, log P of X, plus the summation over all training instances of the log of the sigmoid at the training instance, right? So it has two parts. Does the first part have any model parameters in it? Does it? Yes, no? The second part? So which do I have to maximize? I just need to maximize the second part, right? And so to train my model parameters, I just need to maximize the term that's in blue. So I will find the W0 and W1, which maximize the log probability of the training data, which is just the sum over all training instances of the log of the sigmoid value at the training instance, right? And this, as it turns out, or alternately, I can minimize the negation of this log sigmoid, and crazily enough, this is exactly the same as minimizing the KL divergence between the label and the output of the sigmoid. So when we train our logistic regression classifier, or if you train a single sigmoid perceptron to minimize the KL divergence between the output of the perceptron and the training data, what you're really doing is performing maximum likelihood training. In other words, you're fitting the model, you're training the model to find the best statistical fit to your training data. It's not a blind mechanical procedure. This is actually a statistical optimization problem. Nobody told you that, right? So that's great. We understood this, that we understood how a simple sigmoid is a linear classifier, and how when you train a sigmoid, you're performing maximum likelihood estimation. But then our problem is not linear, right? Our problem is more like this. We're trying to learn a double pentagon decision boundary with a bunch of data which approximately has a distribution where a double pentagon decision boundary could be drawn. what happens here? Now, before we begin looking at this, let's look at the cleaner case, where I can draw a clean boundary, and there are no blue dots on the red side and no red dots on the blue side. Okay? So the net must learn to perform this classification. And we know from lecture 2 that we can actually classify this data using this network, right? Where I have one set of 5, one subnet to determine the first pentagon, the second to determine the second, and then I OR the 2. So let's say I give you the actual architecture of the network, this guy, okay? And say all I say is find me the parameters of the network. That's what you'd just be learning, the parameters of this network, okay? Now, assume the model is learned. If the model is learned, what is this final perceptron? This final perceptron is a sigmoid, right? That's what we do when we perform classification. And what kind of a classifier is a sigmoid? Can everybody say linear aloud? Linear. Right? It's a linear classifier, right? If it is a linear classifier, and let's say this network is doing a perfect job of classifying the red dots from the blue dots, then what can you say about the inputs to the final perceptron? It's a linear classifier and it's doing a perfect job. What can you say about its inputs? They must be what? Can you all say linearly separable? Thank you. You will remember this, right? So it means that out here, those data must be linearly separable, right? So if you look at this data out here, by the time the network has processed the data, it keeps modifying the data. And when it comes to just before the final perceptron, the final softmax, the y1, y2 values when plotted are going to look like this. They are perfectly linearly separable. So what does this mean? It means I can actually separate the network into 2 components, right? The network has one block, and what does this block do? What has this block done? It has moved my data around, right? Until they became linearly separable. So you can think of the lower region of the network as a feature extractor, which has extracted linearly separable features from the data. And then you're passing it through a linear classifier. That makes sense to everybody? So overall, if this network is performing perfect classification, the output of the penultimate layer must be linearly separable. So the rest of the network, shown by the box, can be viewed as a transformation that transforms data from a space where they are not linearly separable into a space where they are, into a space of features where they're linearly separable. And this is not just for the optimal structure. For any network, if the network is doing a perfect job of classifying your data, it means that the rest of the network, everything except the classification layer, has moved the data around so that they are now linearly separable, so that the final neuron can perform linear separation. Now, what if now suppose I go back here, and here, instead of having this network, I remove this neuron. If I remove this neuron, can the network perfectly classify the double pentagon data? Because it has less than the minimal number of neurons for the data, right? You agree? Yes. So what would happen then?
The data would be transformed into a space that's not perfectly linear.
The rest, when you try to train the model is still going to be shifting the data around and trying to make it as close as to linearly separable as possible, and then try to learn the optimal linear classifier for it, except that it won't be perfect anymore, right? It'll fail to separate, but it still attempts to transform the inputs into a linearly separable features. Hold on. Okay, these are easy questions, guys. Who's red owl? Okay, what's the answer to the first question?
True.
Thank you. And who's navy owl? Is there a navy owl in class? There's no navy owl in class. Okay. And there's a navy bear. Who's navy bear? There's got to be a navy bear in class.
It's true.
The second one is also true. Does everybody agree that both statements are true?
Yeah.
Okay, so perfect, right? So the portion of the network until the second to last layer is essentially a feature extraction module that attempts to extract linearly separable features for the classes. And the output layer is a linear classifier that can only perform well if the rest of the network transforms the input space such that the classes are linearly separable, right? Okay, perfect.
So it's developing, like if it was less than optimal, it looked like an SVM.
So if it was less than optimal, the point is if it's optimal, it's going to linearly separate.
Right. But
If it's less than optimal, you're going to have some overlaps.
Okay.
That's exactly, so in a more typical setting for the problem, you're going to have data of this kind, where your double pentagon boundary is not going to cleanly separate things, right? And so what really happens over here is that the network is actually performing maximum likelihood estimation, right? But it's computing, what it's going to do is trying to transform the data. The lower portion of the model is going to try to transform the data so that the posterior probability of the classes can be modeled by a logistic function, okay? It won't be a perfect job. It's not going to be 1 and 0, but it's going to learn a logistic function which gives you actual probabilities. And so when you have n-separable classes with an output from a logistic perceptron, then the output logistic is going to compute the a posteriori probability of the classes from the output of the feature extraction layer. So what do I mean? Here I have the network, except without the classification layer. X goes in, f of x comes out here, and this is your logistic, your softmax. This is the output. So this one is going to learn p of y given f of x, because the logistic is actually seeing f of x, right? But f of x is not distinguishable from x itself, right? So this is going to be the same as p of y given x, more or less. And so what is the network actually learning in this case? The overall network. When you optimize the network, what's it's learning? It's learning to compute the posterior probabilities of the classes. The way it does it is that it first moves the data around into some feature space, f of x, such that a logistic function can now compute learn to compute the posterior probabilities of the classes in that space. But the overall network is still performing maximum likelihood estimation, right? So when you train the network to minimize the KL divergence between the output of the network is still p of y given x. For multi-class networks, it's going to be the vector of posterior probabilities for all the classes. And if you train the network to minimize the KL divergence, the parameters of both the final logistic and the network are learned to maximize p of y given x. So we actually perform maximum likelihood training of the network when you use the KL divergence, right? What if you didn't use the KL divergence? Can you take a guess? Did this make sense? That when we use KL divergence, you're actually performing maximum likelihood estimation. What if we used a different divergence? Anybody want to take a guess? It turns out you're still going to try to approximate this. You're just going to do a crappier job. Okay? So here's your timer name. Okay, guys, this is, 10 seconds. All right, Scarlet Rabbit. What's the first statement? Okay. And Emerald Cheetah, such things exist. Where's the Emerald Cheetah? They don't exist. Okay. Where's the teal turtle?
Here.
Okay, second statement, true or false?
True.
Thank you. Lavender llama. Is there a lavender llama in class? Apparently not. There's a lime zebra. Who's lime zebra? Absent. And navy bear again. Okay, navy bear, we know you're present. Indigo woodpecker. Who's indigo woodpecker? Spring break? No? No. Okay. Who's the coral wolf? This is shameful when I get, Olive tiger. Where's olive tiger? Okay. Mint panther. Everybody's absent. Somebody answer. Is the fourth statement true? Third. Fourth. True. Fifth. Okay, thank you. Someone's paying attention, right? So a classification network is just a statistical model that computes the a posteriori probabilities of classes given the inputs. Training the network to minimize the KL divergence is the same as ML training of the network. And it's, the last one has not actually been stated. But if the features become linearly separable, you could be training it using, you can, for instance, train your neural network and maybe just put in an SVM on the, after the feature extraction. It potentially could give you a better result, right? Yeah.
So on the node SVMs, when we train SVMs, we kind of overcome the non-separability with a slack variable, correct?
Yes.
Why is that not what we use?
You could do that. It's a different loss function. That's it, right? In fact, you can use all of those tricks along with the neural network. So a classification MLP actually comprises two components: a feature extraction network that converts the inputs into linearly separable features, or nearly linearly separable features, and a final linear classifier that operates on the linearly separable features. And using a softmax, the final layer actually computes the a posteriori probabilities of classes, right? So training the network to minimize KL divergence is the same as ML training of the network. Everybody with me? Yeah.
So even the phoneme classifier that we made in homework 1 part 2 follows the same structure of feature extraction and then.
Every single network that you've trained so far.
Okay.
Right? This is a universal statement. Okay, so we figured out what happens in the final layer, right? What about the lower layers? What really happens? Now, we know that the lower layers are actually going to be separating, making the features linearly separable. But how do they do it exactly? And so there's a manifold hypothesis that as you go through the layers, the features become increasingly separable. Now, how exactly does it do it? Here's a very beautiful example that my friend Anders Oland actually designed for me. So we're trying to train a classifier to separate out data in the circle from data outside the circle, right? This is not a linear classification problem. It's a circle. So how are you going to do this? We're using a network here which has just one hidden layer with 3 neurons and tanh activations. Now, my input, here's what happens. My input lies in a 2-dimensional plane, right? What are the actions that happens? In this case, first I'm going to be performing Wx to go to a space Z, right? What is the space? What is the dimensionality of the space Z? Anybody? In this example, what would the weight matrix be for the first layer, for the hidden layer? What is the size? Can someone say it aloud, please? What is the size of the weight matrix? Can everybody say 3 cross 2? Everybody. Yes, it has to be, right? After all these months, you should have that. So if the input is in 2 dimensions, what is the dimensionality of the output? 3, correct? But is it going to take the entire 3-dimensional space? You're not adding information, right? So the input is going to be a plane. Once you transform it, this is actually going to be a two-dimensional plane in 3D space, right? What would happen to this plane then after I put it through a tangent? What happens here?
Plane will start looking like a tangent curve.
This is in 3 dimensions. You're going to get a different tangent value at every location, right? And so this is going to become, instead of a plane, it's going to become some kind of a warped surface. Right? Okay. Then I'm putting it through a different weight matrix. What is the size of the second weight matrix?
1 cross 3.
Can everybody say that aloud? What is it actually doing?
Output.
It's going to be collapsing this whole thing. This weight matrix is actually a single arrow. That's the arrow, right? And your plane is going to be projected onto this line. And so you're going to get points lying entirely on this line. Right? That makes sense? Okay. And then if I apply a threshold, you're basically saying, this is basically going to become a 1D feature. And then you choose some arbitrary point and say everything on one side is going to be my red class and everything on my other side is going to be my blue class. And hopefully this process somehow manages to separate the red from the blue, yes.
Is it mathematically similar to the kernel method?
It's, yeah, you can think of it that way, right? You can think it's similar. But let's look at what is happening over here. Let's look at this training, right? So here, so that first figure to the left, the top left is just showing the loss. Okay. The second figure is showing you what happens to this two-dimensional plane when you put it in 3D space. The third figure shows you how it is warped. The fourth figure shows you what happens when that warped surface is projected onto a line, right? And what the training is doing is trying to figure out how to orient this two-dimensional plane in 3D space such that when you warp it and project it onto a line, all the red dots fall to one side of a single point and all the blue dots fall to the other side. That makes sense, right? It's beautiful. You can actually see how it's operating, right? It's very cool. So again, observe what's happening over here. If I can, where's my mouse? See how it's searching for the right orientation of the plane in the second figure. Left, right? Once it finds the right orientation, when you project it all onto the line, it's ballooned the blue out, the inner region out, so that when you project it onto the line, the blue is on one side and the red is on the other, and you're getting a pretty neat circular decision boundary, right? Very neat, right? So you can see how it sort of manipulates the data to actually make it linearly separable. This is a very simple case where you have just one hidden layer. Here's something which is CIFAR. This is CIFAR 10. We have an 11-layer network over here. And as you go through the layers, see what happens to the data. The different colors are the different classes. This is at the beginning of the training, right? What happened here? You can see that as you go through the training and as you go through the layers, the classes become increasingly linearly separable. In fact, although it's an 11-layer network, the classes are already linearly separable by the 9th layer, and the next 2 layers are just increasing the separation between the layers. This is in 2D. I've shown 2-dimensional projections of this of the features. Here is a 3-dimensional projection, and you can see it once again how, as you go through the layers, all the classes become linearly separable. Very cute, right? And so something interesting. The classes have already become linearly separable long before the final layer. So in fact, if you train the entire network and you threw the final 3 layers away, and then you stuck a linear classifier after the 9th layer, you're still going to get almost perfect classification. So one of the standard tricks for actually making your model smaller. So we get an idea of what's happening, right? As the data go through the network, they're getting more and more linearly separable. And that's the job of the lower portion of the network, is to make the classes linearly separable. And then the final layer can just separate with a linear classifier. And any questions?
This looks very similar to the kernel tree of in the SVM, right?
Okay, tell me what the difference is.
So in the SVM kernel tree, actually we project the question from the low dimension to the higher dimension so that we can find a way to separate the different samples.
Yeah.
Yeah. So it looks very similar.
Okay, so what is the gap? You're right.
Yeah. So yeah, maybe the capability is between the SVM and the neural networks are different.
You're learning the kernel, kind of, right? In an SVM, you basically have to choose your kernel. You don't know what the function is that's going to make these things separable.
Makes sense.
Right? This is actually learning the function that makes the classes linearly separable. And the final classification is not in high dimensional space at all, in fact, right? It was just 3 dimensions. So long as you learn the function, you can actually do a pretty good job. Okay, so we've seen what the network learns at the top. We've seen how it modifies the features, right? But what happens at each layer? Let's go back and look at that. So for that, let's go back and look at the basic perceptron, back to lecture number 1. And I like going back to history. That's your perceptron. I'm going to assume that you have a simple threshold perceptron for now. So you're looking at a weighted sum of inputs. And if the weighted sum exceeds the threshold, the perceptron fires, otherwise it does not fire, right? Now, what does it mean to compute a weighted sum of inputs? The weighted sum of inputs is simply the inner product between the weight vector and the input vector. Summation Wixi can be thought of as W transpose X, where W is the weight vector and X is the input. What is an inner product? What does it compute? It basically computes a cosine, right? So again, I mentioned this earlier. Here's the thing. In high dimensional space, pretty much all vectors are the same length. You may find this to be kind of extraordinary, but as you increase the dimensionality of the space, and if you cap the length of the vectors, then basically you're saying that the data lies within a surface, within a sphere, right? But as you increase the dimensionality of the space, more and more of the volume of the sphere lies very close to the surface. In 700 dimensional space, basically the entire volume of the surface sphere lies within a small infinitesimal range of the scheme of the sphere. So what does this mean? Every single vector is the same length, more or less. The difference in the lengths of vectors is really small. And so when I'm computing the inner product of 2 vectors, the inner product of 2 vectors is simply going to be, what is the inner product of 2 vectors? If I have X transpose W, this is simply mod X, mod W cos theta, right? This is the theta is the angle between the 2. And so if I'm saying that all vectors are the same length, these guys are all pretty much the same length. These guys are all pretty, and this is of course given to you, right? And so if I say X transpose W is greater than or equal to T, if I'm comparing it to a threshold, it means that cos theta is greater than or equal to some T over mod X, norm X, norm W. The weight is a given, so you can ignore it. This is a constant. It's going to, you can ignore this. So you can think of this whole thing as some threshold. Let's call this Q, right? And this is what you're computing, right? So it means that you're saying that the weight vector represents some direction, and the unit is going to fire if the input lies, what does it mean for the cosine to be great? The angle must be small, right? So in other words, you're going to say over here that theta is going to be less than or equal to cos inverse Q. And so if the input lies within some angle cos inverse Q, or some angle of my weight vector, then the perceptron is going to fire. So what does this mean? It means that the weight vector literally represents a typical pattern The weight vector is the pattern that the perceptron is searching for. And if anything, the closer it is in angle to the weight vector, that's when the perceptron fires, right? And so here, when I'm looking at the inner product between two vectors and comparing it to a threshold, the inner product is basically the correlation between the two vectors. So if, for example, you've seen these old LED grids where you have lots of LEDs and in the old digital displays, these things used to be used for watches, right? If you wanted an LED grid and you had an LED grid and you wanted to determine if an input was the number 2, if a pattern was the number 2, what would you do? I can train a perceptron. And what would the weights of the perceptron be like? The weights of the perceptron must be the shape 2, right? That would be the black pattern to the left. And given any input, you're simply going to be computing the correlation between the two, inner product between the weight vector and the pattern that you got. And if this was lesser than some threshold, then you say the two are not the same. If they're greater than the threshold, they're very close enough, I'm going to find, right? So you get an idea of what a single perceptron is doing. It's actually searching for a pattern, and the pattern is specified by the weights of the perceptron, right? Make sense to everybody? Okay. So now let's take a slightly more complex problem. I'm still working with the LED grids, but now I want to train a network to determine if what is being shown on the grid is a digit or not, because I can show all kinds of patterns on the grid, right? So I want a network which looks at this input and decides if it's going to fire a 1 if the input is a valid number and 0 otherwise. What would the lowest layer of the network be doing? Now, at the lowest layer of the network, each neuron is a perceptron, right? And what is a perceptron really doing? Each perceptron is searching for a pattern. The weights of the perceptron represent the pattern it's searching for, right? And so you might find that maybe the weights of the first perceptron end up looking like something like this. The first perceptron is looking for horizontal patterns, right? The weight of the second perceptron may end up looking like something like that. It's looking for a vertical pattern to the right. So each of these perceptrons is going to look for a very specific feature. And if the later perceptrons determine if these features occur in the right combination, and if they do, then maybe the next layer of perceptrons detect the individual digits, and then the whole thing is odd, right? But the point is this. The lowest layer perceptrons are looking for very specific patterns in the input. Okay, so now let me do this, right? Same network. I have the so I've trained this network, okay? And this network is looking at pixel grids. And this perceptron, each of them is looking at the entire input. And this perceptron is looking for this pattern. This perceptron is looking for this pattern. This perceptron is looking for this pattern. This perceptron may be looking for this pattern as well, okay? So I've trained the network. Now I just look at the first hidden layer of the network. And can you wake her up? Maybe she needs to. You want to go wash your face? Okay. So let's say I've trained the network, okay? And now I provide an input and I check if this perceptron has fired, okay? If this perceptron has fired, which pattern exists? The top. So here I draw this guy over here, okay? And if this perceptron has not fired, which pattern doesn't exist? If this one has fired, which exists? So I can go through this new perceptrons one at a time, find out which one's fired, right? And recombine the weight pattern for these guys, right? And what would I get at the output? what would I get back?
If that pattern that exists is a digit,
If the pattern is,
if that pattern is a digit or not.
no, but I'm just taking just the input. So if I just go through each of these guys and keep filling in the patterns that they detected in this box, if they fire, what will happen?
You'll get the pattern of the input.
You're basically going to reconstruct most of the input, correct? So this one fired, this didn't fire, this one fired, this one fired. So I know the input looks like this, right? That makes sense?
Yeah.
Which is the same as saying, if this has a weight W, I can put this W. So I can, every time these things fire, I'm combining their weight patterns with the output over here, which is either a 1 or a 0, and this should more or less reconstruct something that looks like the input. Will it actually reconstruct the entire input in this example?
Probably not,
Why not?
because we're approximating whether how close the input is to that individual pattern. If it's similar enough, then it will fire. Then the first layer perceptron will fire, but it doesn't have to be exact.
Assuming even that it's exact, right? So this will not actually reconstruct the input because we trained, what did we train the network for?
Classifying digits.
To detect if it's an input or if the input is a digit or not. So it's only going to recognize features which distinctly make things digits or non-digits. Any other features that are present in the input are going to be lost, right? So you're going to get back digit-like reconstructions or clearly non-digit-like reconstructions. So the reconstruction is going to be kind of approximate, but you still get the idea. If I still just recombine the weights of the neurons using their own firing patterns, I should be able to reconstruct the input, right? Make sense? Okay. Now I can make this more explicit. Over here, the network is optimized to recognize digits. So it's only going to recognize distinctly digit-like or non-digit-like features. The rest are irrelevant and will be lost. But then I can actually redo this and say, learn all the most important features in the input so that when I recombine them, I can reconstruct the input itself. So this is what we will call an autoencoder, where the network is learning to reconstruct the input. And how would a network, an autoencoder of this kind, be trained? Let's take the simplest one. It has just one neuron, right? So again, the input is a weight vector. It's going to look at, it's searching for some pattern W. And if it finds the pattern W, it's going to recompose that pattern W, right? And it's only a single pattern W that it's looking for. So in this case, if I'm trying to, for simplicity, I'm going to assume that the neuron has a linear activation, right? Just for convenience sake. So if I do this, here's what the output of the neuron network is going to be. The neuron gets Wx. The reconstruction is W transpose X because you're reconstructing, you're reestablishing the W, right? And so you're going to be training this network to explicitly minimize the error between X and X hat, which is to say you're going to be minimizing the squared norm between X and X hat over here, which is X minus W transpose Wx whole squared. Has anybody ever encountered this? What is this optimization? Anyone? This is principal. You guys are supposed to look at the slides, right? This is principal component analysis. I give you the hints. I never ask you a question without giving you the hints. So what does principal component analysis do, anybody? Finds the most important features, but here's what happens. So you're in PCA, you're given some data. You might be given some data. Typically, I'm going to assume it's zero mean, so just PCA is for zero mean data, but anyway. And then you're trying to find a direction such that, what does W transpose W do? It's actually projecting it onto the vector W. And it's trying to find the vector W such that the error due to projection is minimized, right? And so at each point, what the encoder is doing is determining this length. What the lower portion of the network is doing is determining this length. And then the reconstruction is simply multiplying the length by the weight vector W. And so what will happen here is that it's going to find the vector W such that when every input is approximated at some point on this line, the total error is minimized, right? Now, the key characteristic of this over here is that if I train this network and find the W to minimize this error, if I subsequently get rid of the entry portion of the network, what can the output of this network, what can this portion of the network reconstruct? Every point that it comes out of this is some scaling of W, right? Because regardless of what I feed it here, as you've got some W going in, any value Z can come out, and this output is going to simply be WZ, right? So WZ is simply going to be a point on this line. Regardless of what the input is, the output is always going to be on this line, right? This is the principal component, the principal direction. This is classical principal component analysis. This is when I have only one hidden neuron, right? If I have multiple hidden neurons, right? So over here, simply varying the hidden representation is going to result in an output that just lies on this line. And now, if I have multiple hidden neurons, then depending on the number of hidden neurons, I'm actually going to be constructing my weight matrix represents a plane. I'm finding a plane in the high dimensional space such that when all the data are projected onto this plane, the total error from the projection is minimized. But the reconstruction, regardless of what the input is always going to be on the, where's it going to be? Pardon me? The weight. So again, observe that the reconstruction is always going to be of this form, right? WZ. So what does WZ look like? It's just going to be a hyperplane, the pink plane, right? Regardless of what the input is to the network, the output is going to be on the hyperplane, right? And so you're finding what the network is doing, the weight matrix is doing is to find the hyperplane such that when you project all the training data onto it, the error is minimized. And then subsequently, if I just take the upper portion of the network, this guy, okay, the upper portion of the network, regardless of what I feed the network at this point, from here on, the output is always going to be on the plane, okay? So here's the point. Mm-hmm. Yeah, what are the questions? It doesn't matter, right? What you're minimizing is the error. So the question is, would you expect the same behavior regardless of the training technique? The point is the output is always going to be WZ. So this means that you're always learning to reconstruct a hyperplane. And regardless of the training technique you use, what you're eventually doing is trying to find the hyperplane such that the error of projection is minimized, right? What is the second question?
We always define the number of patterns based on the number of patterns. And do we even know those patterns?
So this is going back to the digits example. Do we always determine the number of perceptrons based on the number of patterns? Do we know these patterns? We don't. So we like to have as many, we like to make the early layers wide because you want to detect as many patterns as possible. Okay. Yeah.
This collapse to W. In that case, would the features be meaningful?
Wouldn't this collapse too?
W transpose W going to 1. In that case, would the features be meaningful?
So it doesn't matter. The features are eventually, what you're saying is that the output is WZ, right? If there's some Z going in, the output is WZ. Even if you say the input is not W, but some U, right? Eventually, you're always reconstructing WZ. And so since you're minimizing error, you're finding the W such that for every input X, there's a Z, such that WZ has the lowest error with respect to X. So you're still finding the principal hyperplane. Okay, who's bronze bear? Is there a bronze bear in class? Okay. Who's the red zebra? Okay, the entire class is absent. What's the answer to the first question, guys? Okay, red zebra, what's the answer?
First answer is true.
Okay. And who's Mint Wolf? Mint Wolf is absent. And Olive Woodpecker. I'm sure there was an Olive Woodpecker in class. Okay, somebody answer the second question. True or false? Okay, beautiful, right? And so an autoencoder with linear activation performs principal component of the input, analysis of the input. And an autoencoder with linear activations of the hidden layer that has been trained on some data can only output values on the principal hyperplane that it has learned, okay? But yes. Hyperplane can be, depends on the number of hidden neurons, right? So if I increase the hidden neurons here to 4, it's going to be a 4-dimensional plane. If it's 20, it's going to be a 20-dimensional hyperplane, right? Yeah. Okay. So any other questions? Yeah.
That previous question was asking if, like, is it a problem that WT times W would become an identity matrix? But isn't that you want?
No, WT times W doesn't have to be an identity matrix. And it's in principal component analysis, we typically set that to be a constraint because, yeah. Otherwise, there's going to be a scaling issue. Yeah. In PCA, that's just an additional constraint that you impose. Okay. Anyway, so terminology. The portion that of the network that's actually determining the hidden representation, I'm going to call that the encoder, and the portion that reconstructs the input from that hidden representation, I'm going to call that the decoder, right? And so when the hidden layer has a linear activation, the decoder is only, or when the decoder actually has only linear activations, then the decoder is only computing W times Z, right? So if the decoder has only linear activations, it can only reconstruct data on a linear hyperplane. What happens if the decoder includes neurons that have nonlinear activations? Remember what happened when we had a tanh? It took the surface and warped it, right? So when the decoder has nonlinear activations, it's actually learning the equation for a curve. And what kind of curve is it learning? It's learning the equation for a curve such that when all the data are projected onto this curve, the total error is minimized. And what is the encoder doing? What's the encoder doing? Over here? It's trying to, yeah.
Learning a compressed version of the inputs.
The encoder is learning to project it on the curve. So here's the way to think about it. And we'll see some more examples. If my data, for instance, have a distribution of this kind, then the decoder is going to learn this surface such that when every data point is projected onto the curve, the total error is minimized. And the encoder, now observe that every data instance is being projected onto a specific point on the curve. The encoder is learning where on the curve the data point must be projected. So the encoder is learning to project the data point onto the surface, and the decoder is learning to reconstruct the surface. To give you a better idea, here's a nice example. This is this is basically nonlinear PCA. The moment you begin introducing nonlinearities in the model, it becomes nonlinear PCA. Okay? And deeper networks can capture more complicated surfaces, and so they give you more complicated manifolds. So whenever you have an autoencoder with nonlinearities in the decoder, you're basically learning the equation of some surface such that most of the data lies closest to this surface. You're learning the equation for the surface. You're learning to construct the surface that represents the overall layout of the data. So here's an example where we've trained a network using data from this helix, the dots, right? What is the surface that captures the structure of this helix? It's a helix, right? It's a spiral. So that means that if you train this model properly, the decoder should be reconstructing the spiral. The encoder is going to be finding the point position on the spiral. So here, you have a spiral of this kind. And then if I start from here, I can measure the distance going out, right? Along the spiral. And so the encoder is finding the distance along the spiral. That is the Z. And then when you feed the Z into the decoder, it's actually finding a location on the spiral for every data point. Does that make sense? Right. So it's projecting the entire data onto the spiral. Except, of course, it doesn't behave as cleanly as you would like to, depending on the training data. It didn't actually, as you can see over here, it didn't actually learn the spiral. It learned something like this. Something crazy you can see about how it goes. And something else that you see. At some point, it runs out of training data. And when you go beyond the training data range, so there's a range of Z values, the hidden values that you get from the training data. And those Z, so long as you stay within the Z values, the reconstruct data are going to keep falling on the spiral. If you go outside that range, it goes off the spiral, as you can see, right? Or here's another example.
So, real quick, how do you determine the breadth of the layers between your encoder and decoder?
So in this case, I knew the answer, right? I know that the underlying manifold is a curved one-dimensional manifold. Otherwise, we're guessing. So here's data from a sinusoid. Again, the same network. This one has, I forget, the decoder. I think I have the exact information over here. This is an MLP with 5 residual blocks, 64 hidden units, but the actual autoencoder has only one neuron for the final hidden state. And so here again, you can see that the decoder is learning the structure of the sinusoid. And the cool bit is that now, regardless of what input you give the decoder, the output is always going to lie on the sinusoid, right? And so you can actually put that to some use. So when the hidden representation is of a lower dimensionality than the input, often called a bottleneck network, it's going to learn TCA. It learns the manifold of the data if properly trained. And more importantly, now the decoder can only reconstruct data that actually lie on this manifold. Right. Let's see a practical example of this, and I don't know if my audio will play, so I'm going to hope it does. But suppose we trained an autoencoder on digits, right? The digit example that we saw earlier. Then I throw away the encoder, and I feed the decoder random inputs. It's going to learn the manifold of digits. Pretty much everything that comes out, regardless of the input that you give the decoder, is going to look something like a digit, right? Or here's a example where, let me see if my sound plays. Paul, can you have the sound play? Okay, thank you, right? So in this case, we learned an autoencoder on a bunch of clarinet sounds. And then once I throw away the encoder, the decoder has learned the manifold of clarinet sounds. Regardless of what I feed into the decoder, it can only produce sounds that kind of sound like in this case, this is a saxophone, right? And so we've trained this autoencoder on sax sounds. And now, in this case, I just gave it an input where the first neuron had a value 0, 1, and the rest of them had value 0. And we just learned. It produces something that sounds like a saxophone. A different input to the same decoder. Why? Right, so it seems to learn. So the point is, if I change the input of the decoder, this is strange. Well, it worked once, right? Here's another example. This was with a clarinet. Right? A completely different input at the hidden layer. So it's not producing random noise. That's the key piece, right? It has actually learned the manifold of the space in which these sounds lie. So if I just take the decoder and then excite it with different sounds, it's always going to generate some data that kind of resembles the original source that it was trained from, which is pretty impressive, right? If you think about it, it learns the structure of the data, right? And let me put this to some use over here. First, here's a point. Who's the next? So Mint Hippo, be prepared. Okay, you know what? I'll spare you guys. Can somebody answer the first question? Is the first one true or false? Second, true or false? Or somebody on Zoom, is the third statement true or false?
True.
What about the fourth?
True.
Okay, so an autoencoder with nonlinear activation performs nonlinear principal component analysis. It finds a principal manifold which may not be linear, near which the training data lie. And the decoder of the nonlinear autoencoder can only generate data on the principal manifold, regardless of the input. And this is what we saw in the clarinet and the saxophone examples. So you can think of this decoder of this autoencoder as some kind of a dictionary, which is able to generate data of the kind that was used to train the autoencoder. Again, this is only the decoder, right? What is the encoder doing? The encoder is finding the position on the manifold. The decoder is taking the position and translating it to a full dimensional state, right? So here's a cute little application. I played around with sound and music for many years. This is an old example, but it conveys the idea. You're given a mixed sound from multiple sources. You want to separate out the sources. So, a standard, you got a recording which includes guitar and drums. You want to separate the guitar from the drums. How would you do it? A standard approach, you learn a dictionary of building blocks for each source. So you got a bunch of data for the guitar, and you learn what guitar sounds sound like. And then you'll get a bunch of training data for the drums. You learn what the drum sounds sound like. And then when you get some mixed data with guitar and drums, you want to see how these two dictionaries can be composed to create the example that you just heard, and then you can use this to separate things out. In our example, right? So in our case, what do we do? I have a bunch of training data for the guitar. I train an autoencoder for the guitar. I have a bunch of training data for the drums. I train an autoencoder for the drums, okay? So now, if I look at the decoder over here, this decoder can only produce guitar-like sounds. This decoder can only produce drum-like sounds, right? Now later, if I get a mixed recording, which includes both guitar and drums, I'm going to try to explain it in terms of the sounds that the guitar and decoder can generate and the drums decoder can generate. So the input is going to be my mixed recording with the drums and the guitar. Now these decoders have already been trained from training data, these guys. And what I will try to determine is what must the input to this guy be and what must the input to this guy be so that when I sum their outputs up, it sounds like this mixed music that I just heard. Right, and how can I find these inputs? Anybody? Anyone? Somebody on Zoom? I can just use backprop, right? Backprop can not only learn the weights, it can also learn the optimal inputs. If you can either fix the inputs and learn the weights, or you can fix the weights and learn the inputs. Correct. Here I fixed the weights. And so I can use backprop to learn the inputs and find the inputs such that with these, the inputs that I've determined can be combined to generate the sound. And then subsequently, if I just look at what this guy alone generated, that's going to be the first sound. What the other guy alone generated is going to be the second sound. Easy enough. That make sense? To all of you? Right. Let's see if this works. And this is where luck. sound. Non-separated sound. Not a particularly complicated model, right? But again, the whole point of the example was to show how the simple autoencoder model actually learns the manifolds for the individual sources. And here I actually used the characteristic that the model that has been learned in this manner can now only generate the first instrument for the first encoder. It can only generate the second instrument for the second encoder. And then I can figure out how these decoders can be excited to such that their combined outputs sound like what I just, my mixed sound. And then the outputs of the individual encoders give me the separated sound, which is kind of cool. So, there again.
What's the original?
This is the original. This is a separated one for the first guy. There's a little bit of again, you can do much better than this, but those models get a lot more fancy than what I just showed you, right? This is about 20 lines of code. And some training data, maybe half an hour of training data for each source, but still 15 minutes. But anyway, the point is, we learned a few things today. Classification networks learn to predict the a posteriori probabilities of classes. The network until the final layer is a feature extractor that converts the input to be almost linearly separable. And the final layer is a classifier that operates on linearly separable data. But neural networks can also be used to learn the structure of the data. I basically learn the nature of the manifold on which the data lie. Nonlinear principal component analysis. So these were autoencoders, and this can be used to compose constructive dictionaries for the data, which can be used to model data distributions. We're going to pick up on the second aspect in the next couple of lectures where we talk about variational autoencoders. Any questions? Yeah.
In music, when we talk about a different instrument, we kind of use the same node, but they're different instruments. So how do we make sure that
Because they're just going to have the, if you look at the fine detail of the spectral structure, there's enough difference. So they actually end up being on different manifolds. And the model actually learns, you can learn these models so that, these manifolds are distinctively different.
Where the signals or frequency space.
Okay, thank you, everybody.
Maybe using